A few words about the variance covariance matrix. So in R it is very easy. It just takes in the data and has appropriate libraries to do the work for you. Now if you have a n by n identity matrix as the covariance matrix, then you know that the random variable, this is normally distributed with mean 0 and variance 1 for each of the variables. So this is standard multivariate distribution in which all the variables are independent of each other. So you could have a bunch of variables, say xt, yt and zt, but all of them are drawn from the same normal distribution. There is no covariance as such between them. They're independent of each other. So for that you have this distribution, and I have explained this in my probability lectures. If you multiply this random variable z, which is a vector of normal random variables, then you get a new matrix which is normally distributed, mean 0, and variance now is A times A transpose. So this is the variance covariance matrix. So to find out random variables drawn from a matrix which has a specified variance covariance matrix, you first need to decompose this variance covariance matrix into A times A transpose, and then you take just this A and multiply it with Z to get the required random variables. So what I mean is, you take a normally distributed bunch of random variables, say 3 of them, and then you multiply these 3 random variables. So say I have taken 3 random variables, x1, x2, x3, all from this, and then you can multiply it with some matrix A, and this will give you correlated random variables which have the correlation matrix as sigma. So the idea is that you don't have to do much work. If you once you implement drawing a normal random variable from this distribution normal 0 1, then you can get any correlated random variable. So any matrix sigma is given to you, you can get correlated random variables simply by multiplying this vector of 0 1 random variables with A, where A times A transpose is sigma. Now this is obtained through Cholesky decomposition. In fact, this is one of the favorite questions in quant interviews. What is Cholesky decomposition? And you can say the Cholesky decomposition is used to find something like this. So this is important because if you have to implement this in C++, you need to know how do you get correlated random variables given a correlation, this variance covariance matrix sigma. So that is it. There are just 3 more points which I want to make. First is, it is not possible to truly generate random numbers. So by definition, the random numbers are not possible to generate. So they are so random that you cannot generate them. So the random numbers have 0 probability of getting picked out. So all processes which we make or code in computer to generate random numbers do not truly give a random number, and you have to keep this in mind. So there are large number of techniques to generate random numbers, but none of them are correct. And R is very careful. R is a statistical package. It has been specifically designed by thousands of people all over the world which have contributed bits to it to make random number generation very possible. So this is state of the art. R is state of the art, and there are thousands of algorithms in C++ also. For example, there is a book called Numerical Recipes in C, which you can have a look at to see how to generate random numbers in C++. Now another point is, you can feed in as big a covariance matrix you want to. You can feed in a 2000 times 2000 covariance matrix into your computer. You just have to buy a bigger computer, because you can find covariance between any 2 sequence of numbers. So give me 2 sequence of numbers, you can find a covariance between them. But feeding in extra variables is only going to add this extra noise, because what happens is that when you're feeding in more and more variables here, it is getting multiplied by a matrix, and a correlated random variable is nothing but taking these normal random variables in 0 1 and multiplying them with this big matrix A. If you have more and more components in A, what you're getting is that you're getting more and more noise. You're getting these unnecessarily adding more variables to it, so you're getting more noise. So that it is important that you cluster items which you think are correlated in the real sense, because if you're given two series of numbers, you just put a formula of covariance to it, it will spit a number. So for example, you can give a justification for, say, Microsoft stock is linked to iron consumption, and you can say, you know, if the economy is booming, people are consuming more software and people are doing more construction, so they're using more iron, so in some sense these are related. Then you can find a covariance between these two. So you can find covariance by anything, but a standard logic would be that if someone needs iron, can you give them a Microsoft CD and say, now make use of the CD? Or if someone needs to load Microsoft Office onto the computer, can you give them a block of iron and say, load this into your computer and it will work? If the answer is no, then you should probably not use them in the same matrix. So the idea is that there are some things which are substitutable. Obviously you can have a covariance matrix for pig iron, wrought iron, even aluminum. You know, sometimes you can replace iron with aluminum if aluminum becomes really cheap, or aluminum and copper. But it does not make any sense to have iron and gold in the same matrix, especially in today's scenario when gold is actually a store of value in the times of uncertainty. So this thing you have to keep in mind. Large number of places would just people can just keep on finding covariances between two sequences and keep on building bigger and bigger matrix, and that is not serving any purpose whatsoever.